Okay, in the last couple of videos, we've been talking about polynomials and how to find all their zeros, solve them out using all those different theorems like the factor theorem, the remainder theorem, and all of that. Now we want to look at polynomials from a graphical perspective and figure out how to actually graph them. Meaning, suppose we have this polynomial right here. F of x equals x plus 2 squared times x minus 1 cubed times x plus 7. I wrote it in factored form just because it's a little bit easier to interpret when we get to our problem solving later on. But essentially, that's definitely a polynomial. You can count the powers of the terms to figure out the degree. So 2 plus 3 is 5 plus 1, 6. So that, if you FOILed it all out, would be a 6-degree polynomial. Now we actually want to be able to graph it. And as far as it goes, there's two things that matter when we graph. There's the end behavior, and there's the behavior around the zeros. And we'll essentially combine those two things, and then we'll have our graph. First off, for the end behavior, there's kind of a trick to this. We all know what the graph of x squared looks like. It's a parabola, no big deal. Suppose you wanted to graph, if this is x squared, suppose you wanted to graph f of x equals x to the fourth. Well, if you're not sure what the graph looks like, we just plug in points. If you plug in 0, you'll still get 0, just like the regular parabola. If you plug in 1, you'll get 1 to the fourth, which is 1, just like the regular parabola. If you plug in 2, for the x squared graph, at 2 you get 4, say right here. For this one, when you plug in 2, you get 2 to the fourth, 16, which means you're way up here. If you plug in 3, for this one, you get 3 squared, 9. For this one, you get 3 to the fourth, 81, which means you're like up there by the ceiling or something. But essentially, the idea is it starts off looking like a parabola, and it just gets steeper. The other side of the graph, well, these are even powers, so it'll just mirror that. So it'll do the same thing. It'll just shoot up like a parabola does. And we're not going to take the time to do a lot more of them, but the simple trick that's going on here is, if you look at the degree of this x to the fourth, it's an even degree, and the graph ends up kind of looking like a fourth-degree polynomial, second-degree polynomial, quadratic. If we did x to the eighth, well, it would actually look the exact same. It would just be even steeper. So as far as it goes, when you look at the degree of something like this, if it's even, it just kind of looks like x squared, which is even. But then if you kind of expand on that a little bit, well, suppose you wanted to graph f of x equals x to the fifth. Well, really quickly, at 0 you get 0, at 1 you get 1, at 2 you get 32, and it kind of goes like that. At negative 1 you get negative 1 to the fifth, which is negative 1. At negative 2 you get negative 2 to the fifth, which is negative 32. And it goes down like that. And again, we see that's pretty much just like a cubic. Cubics are odd degree, this is odd degree, and that's pretty much how it works. If these are odd degree, if x is raised to an odd degree, it looks like a cubic, the odd degree one. And that kind of helps us when we want to look at the end behavior of a polynomial, because there's kind of a trick going on. Suppose you have another polynomial, say f of x equals x to the fifth plus x cubed plus 7x squared minus 9. For the sake of argument, suppose I wanted to graph that. Well, if I wanted to find the end behavior, that's the behavior when x is really big approaching infinity or really small approaching negative infinity. And if you're not sure what's going on, we can just plug in points. But if you plugged in points, say we plugged in 10, you would get 10 to the fifth plus 10 cubed plus 7 times 10 squared minus 9. And we don't actually need a calculator for this, we just care about the idea. 10 squared is 100, 10 cubed is 1,000, 10 to the 5th is 100,000. Out of those three terms, which one affects my graph the most? This one, the highest power of x. If you want to see it more clearly, let x be bigger. Let x be 100. Then you get 100 to the 5th plus 100 cubed plus 7 times 100 squared minus 9. And again, here, if you actually solved this out, 100 squared would be 10,000. 100 cubed would be 1,000,000. 100 to the 5th would be, I think, 10 billion at a quick guess. But the point is, as x gets larger, the highest power of x in my polynomial dominates what actually happens to that graph. But the highest power of x is really just the degree. That's 5th degree, that's 5th degree. And essentially what that means is, if I want to graph my polynomials, all I do is find the degree. If the degree is even, then the end behavior will look like the end behavior of a quadratic, like a parabola. If it's odd, the end behavior will look like the end behavior of a cubic, which is down, up from your perspective, down this way, up that way. So as an example, for this one right here, we said this is 2 plus 3 plus 1, that's 6. This one is degree 6, which means if we wanted to graph it, the end behavior of a 6th degree polynomial will look like the end behavior of a quadratic, because that's even degree. Quadratics end like a parabola going up and up. And that's it. I'm not going to take the time to draw out, and I also won't have enough room to draw out all possible end behaviors, but if you think about it, if you have an even degree, either both arrows go up, or if your leading coefficient is negative, we know from transformations that would flip it, and both arrows would go down. If it's cubic, it'll go from down to up, just like a cubic, or if the leading coefficient is negative, flip it, and it will go from up to down. As far as it goes, that's all possible end behaviors, and that's all we need to know. Look at the degree of your polynomial. If it's even, make it look like a parabola. If it's odd, make it look like a cubic. And if the leading coefficient is negative, flip the arrows. And that's it. The other thing we care about is behavior around the zeros. And there's a simple trick to this that we're going to use repeatedly, so I'll explain it several different ways. Essentially, we wrote this in factored form so we could see the zeros. That one is negative 2, so we'll say it's right here. That one is positive 1, say it's right there. That was x plus 7, so that's at negative 7, we'll say it's right here. And I guess I'll shift my arrow over so it'll line up better. And now, essentially, it's pretty much just connect the dots, just like when you were a kid. This graph is continuous, which means I can draw the whole graph in one continuous motion without having my pencil leave the paper. So all we do is we start here at the end behavior. Ultimately, I have to come down because I have to hit my 0 right there. Once I hit the 0, there's two possibilities. I'll either cut through the axis or I'll bounce off the axis. To determine which one you do, you just look at the power of that 0, the degree of that 0. This is negative 7, which is x plus 7. That's degree 1. It's odd. Anytime your degree is odd, you cut through the axis, so we're not going to bounce off. We cut through the axis, or another way of saying it is, if your degree is odd, the sign of your function switches around the 0. This goes from positive to negative, because that's degree 1 odd. But since this is continuous, if it goes down, eventually it has to come up and hit this 0. Then we do the same thing. Negative 2 is the factor x plus 2. The degree here is 2. That's even. If the degree is even, you don't cut through the axis, you bounce off of it. So we just turn around and go back down. Again, there's two different ways to say it. Either if the degree of your 0 is even, you bounce off the axis, or if the degree of your factor is even, the sign of the function stays the same around the 0. On this side of the 0 it's negative, on that side it's negative. It doesn't change. Here it changed from positive to negative because it was odd degree. Here it stayed the same, negative, negative, because it was even degree. And that's all we need to know. Keep doing the same thing. I can go down, but eventually I come back up and hit 1, x minus 1. The degree is 3, that's odd. If it's odd degree, the sign switches around the 0, or we cut through it. So we'll just go up. But then that's good, because there's no more zeros, so I don't go down. So I just keep going up, and I connect to the other arrow, which I have to do. And there's my graph. One thing I will point out just as an aside, and you will actually notice this if you look in your book, if the degrees are odd, if the degree is odd of degree 1, you just cut through the axis. If it's odd of higher degree, like this is degree 3, it's odd but higher than 1, you cut through the axis, but you also change concavity, which means technically here my concavity would switch. For the purposes of this class, we don't really care about concavity, so I'm not really worried about that. I just care about the odd and even degrees. When we get to higher level math, like calculus, then we'll deal with concavity then and kind of look at different properties of it and how it works. For right now, all we really need to know is the end behavior. It looks like a quadratic or a cubic, or one of those flipped. And behavior around the zeros. If the 0 is odd degree, cut through the axis. If the 0 is even degree, bounce off. I'm going to stop the video right now, but then I'm going to make another one really quickly with 1 or 2 examples of this, just so you can see several more worked out.